SwayamPrabha.
In the last class, we have seen a primal dual schema based approximation algorithm design, and that concludes our second part, which is on approximation algorithm. Now, in the next couple of lectures, we will see another way to tackle with the hardness of NP completeness, and that is parameterized algorithm. So, parameterized algorithms. So, what is the drawback of approximation algorithm? Although the runtime of the algorithms were polynomial time, the algorithms were efficient. It failed to give an exact solution. Does not provide an optimal solution. Okay. Now, in many instances, often real life instances have extra structure which may allow us to design an exact algorithm even fast. Real life instances often have extra structure which may allow us to design efficient exact algorithm. Now, with this goal in mind, what parameterized algorithm does, this framework of parameterized algorithm uh, sort of to model this extra structure or extra information, the input consists of two parts. One is the n, which is the length of the input, and another is parameter. So, unlike classical complexity framework, in the framework of parameterized algorithm, the input also comes with a numerical parameter okay. So let n be the size of input instance and k be the parameter. This parameter could be anything. For example, for a vertex cover problem, the parameter could be the size of the vertex cover that you are looking for. For max cut problem, the parameter could be the size of the max cut that you are looking for, or it could be the structural parameter. For example, for the vertex cover problem, the parameter could be the highest degree of the graph, or the size of the minimum cut in the graph, or any other structural parameter, or the chromatic number of the graph, and so on. So anything, and so each of when the same problem with different parameters are different problems in the parameterized world. So, and what we are looking for example, the vertex cover problem can be solved can be solved you know if you are looking for a k size vertex cover, and then we can simply iterate over all n choose k subsets of vertices and check whether it's a vertex cover or not. So in this much time, which is like big O of n to the power k times poly n. And this is typical. For example, why vertex cover only? For example, clique, independent set, or typical problems can be solved in n to the power k time. But this sort of time where the parameter sits in the exponent of n or polynomial in n, these are called XP algorithms. So, algorithms with runtime big O of some n to the some f of k times poly n algorithms with runtime this is called an XP algorithm. Okay, but this is not what we are looking for in parameterized algorithms. So, what in parameterized algorithm, what we are looking for is called fixed parametered tractable algorithm. In short, FPT algorithm. So what is an FPT algorithm? An algorithm with runtime f of k times poly of n for a parameterized problem is called an FPT algorithm. For any computable function f. Okay. So example. So here is a theorem. There is an algorithm for the vertex cover problem which runs in time big O of 2 to the power k times poly n. So what is the algorithm? Proof. It's a search tree based algorithm. What it does is that it picks an edge because that edge needs to be covered, and that means that one of its two endpoints must be picked in the solution. So it picks both the one of its endpoints and tries. So pick an uncovered edge u comma v and recursively solve suppose G is the input graph. So let G be the input graph. So recursively solve, you pick u from G, G minus u, and this deletes all the edges which are incident on u. In fact, that means it deletes all the edges, it removes all the edges from G which are covered by u, and in the remaining graph I am looking for the a vertex cover of size k minus 1. Now you see that input consists of two things. One is the instance and another is parameters. The parameter value also drops. So recursively solve this and you try both the possibilities and this and return yes. Yes means yes, there indeed exists a vertex cover of size k in the graph G. So return is if any branch return is okay. And so what will be the base case? Base case is if k equal to 0 or if k is negative, then we cannot have, or if k equal to 0, then there must not be any edge. If k equal to 0 and there is an uncovered edge u comma v, then return no. So pictorially, I have a graph G, and in this graph I am looking for a vertex cover of size k. I am asking, is there a vertex cover of size k? So it is a graph, and there is a edge which is uncovered between u and v. What I do is that I try picking both one at a time. So I go to G minus u, and in that graph, after deleting u, I am looking for a vertex cover of size k minus 1 and G minus v. In this graph, we are looking for a vertex cover of size k minus 1 and so on. Now, what is the depth of the tree? The depth of the tree is at most k. If at some point the budget k is non-negative and there is no edge in the graph, then it is yes. So here also let me write, if no edges, then also return yes. Otherwise, if there is an uncovered edge and if k equal to 0, return no. So this height is at most k. So right, height of the search tree is at most k. Why? Since the size of the vertex, since the budget, which is the size of the vertex cover we are looking for, since the budget drops by 1 in every level. So height is at most k and the search tree is binary. Hence, the number of nodes in the tree is at most big O of 2 to the power k. Okay. Now, what is the computation in each node? That computation is this, that checking if there is no edge, and if budget is 0, then return no if there is an uncovered edge. This is the computation at every node. Clearly, the computation at every node takes order n time. Hence, the runtime of the algorithm is big O of 2 to the power k times n. So, this is an FPT algorithm. Hence, there exists a FPT algorithm for the vertex cover problem parameterized by the size of vertex covered we are looking for. Okay. Also, a corollary of this algorithm is that if the size of the minimum vertex cover is big O of log n, then such a vertex cover can be found in polynomial time. If the size of a minimum vertex cover is big O of log n, then minimum vertex cover can be computed in polynomial time. Okay. Next, what we see is a faster algorithm, faster FPT algorithm for vertex cover. So, a faster FPT algorithm for vertex covered. So for that, we observe that if the maximum degree of of any vertex in a graph is 2 or at most 2, then the vertex cover can be computed in polynomial time. So here is a observation. If the maximum degree of any vertex in the graph is at most 2, then now let me write of every vertex, then a minimum vertex cover can be computed in polynomial time. Okay, how? First observe that under this assumption, if the maximum degree is 2 or at most 2, if the maximum degree is at most 2, then the graph is a collection of paths and collection of is a disjoint collection of paths and cycles. That means this looks like the graph there are some paths and there are some cycles. Now for paths and cycles, the vertex cover clearly can be computed, the minimum vertex cover can be clearly computed in polynomial time. Now clearly the vertex cover, the minimum vertex cover, minimum vertex cover for every path and cycle can be computed in polynomial time. And what is the minimum vertex cover of this graph? It's a union of minimum vertex cover of each connected components. That means for each path and cycles, you find the minimum vertex cover and take disjoint union, that is the minimum vertex cover of the whole graph. Okay, so let's stop here and we will see in the next class how using this we will be able to design a much faster algorithm for finding a minimum vertex cover. Okay.